Right now, stretched across the sky above you, there is a structure so large that our entire galaxy is smaller than a single bead on one of its threads. It has been there since long before the Sun, since long before the Earth, since long before the first atom of you was forged inside a dying star. And until just a few months ago, almost no human being had ever actually seen it. We knew it was there the way you know a room is there in the dark, by feeling for its furniture, by tracing its edges with our hands. But we had never turned on the lights. Now, finally, the most powerful telescope ever built has looked directly at the largest structure in existence and shown it to us in full. And what it revealed is not the quiet scaffolding we expected. It is something that feeds galaxies and starves them, and bends them, and decides which ones live and which ones die. So what does it mean to learn that you have been living your entire life inside something this vast and never known it was there? Get comfortable and settle in. Subscribe if you have not already, and stay with us tonight, because the structure we are about to explore reaches all the way down to the shape of the galaxy you call home. Let us get into it. Part 1. The Invisible City. There is a structure above you right now that is larger than anything else in existence, larger than any galaxy, larger than any cluster of galaxies, larger than any single thing you could ever point to and name. It stretches across the entire observable universe, billions of light years in every direction, and it has been there since long before the Earth formed, long before the Sun ignited, long before the first atom of you was assembled inside some ancient dying star. And until just a few months ago, almost no one had ever actually seen it. We knew it was there the way you know a room is there in the dark, by bumping into its furniture, by tracing its edges with your hands, by inferring its walls from the way sound moves inside it. But we had never turned on the lights. We had never simply looked at the thing itself and watched it resolve into focus in front of us. That changed recently, and what we found when the lights finally came on is the subject of everything we're going to talk about tonight. The structure is called the cosmic web, and the name is almost perfect, because that is exactly what it looks like. Imagine a spider web, the kind you find stretched across a doorway on a cold morning, beaded with dew so that every strand catches the light. Now imagine that web is not made of silk but of galaxies, billions of them, strung along threads that reach across distances so vast that light itself, the fastest thing there is, takes hundreds of millions of years just to travel from one knot in the web to the next. Where the threads cross, where they tangle together into bright dense knots, you get clusters of galaxies, thousands of them pressed into a single region, and between the threads, filling most of the volume of the universe, you get the voids, enormous bubbles of near-perfect emptiness, hundreds of millions of light-years wide, where there is almost nothing at all. That is the shape of everything. That is the architecture of the universe at the largest scale we can perceive. Not a random scattering of galaxies tossed across the dark like grain thrown across a field, but a vast, organized, interconnected network, a web. And the strangest part, the part that I want you to sit with as we begin, is that for the entire history of human astronomy, this web was almost completely invisible to us. We built telescopes that could see individual stars and galaxies tens of millions of light years away. We mapped the surfaces of planets and the rings of distant worlds and the violent hearts of exploding suns. And all the while, the single largest structure in the universe, the thing that organizes literally everything, was hiding in plain sight, too faint and too diffuse for us to make out. It is a little like living your whole life inside an enormous building, without ever once being able to see the walls. You know there are rooms, because you can see the furniture sitting in them. You can see the lamps and the chairs and the tables scattered across the floor in clusters, but the walls, the corridors, the actual structure of the building, the thing that decides where the furniture can and cannot go, that remains invisible. You would have no idea you were standing inside a designed space at all. You would think the furniture was just sitting wherever it happened to land. And that is precisely the mistake that astronomers spent a century making about the universe. We looked at the galaxies, the bright furniture of the cosmos, and we did not see the web they were arranged on. We could not see the walls. And here is the thing that makes this story worth telling, the thing that turns a piece of cosmology into something that should genuinely unsettle you. When we finally did turn on the lights, when we finally got our first clear look at the web itself, we did not just find a pretty piece of cosmic scaffolding. We found something that is doing things. We found a structure that is not passively holding galaxies in place, but is actively shaping them, feeding some and starving others, deciding which galaxies grow massive and which ones wither, deciding which ones keep making new stars and which ones go dark forever. We found, in other words, that the web is not the stage on which the drama of the universe plays out. The web is one of the main characters, and we, sitting here on a small planet orbiting an ordinary star, are living inside one of its strands. So that is where we're going tonight. We are going to look at how this web was finally seen, after all these years, by some of the most powerful instruments ever built. We are going to look at 5 separate discoveries made in the last year or so, each one using a different kind of light, each one revealing a different way that this web reaches into the lives of galaxies and changes them. And by the end, I think you will come away with a new picture of where we actually live, not just on a planet, not just in a galaxy, but inside a vast and ancient structure that has been quietly deciding the fate of everything for as long as the universe has existed. Get comfortable. This is a slow one, the kind of story that rewards patience, and it starts with a simple question. If the web is everywhere, and it has always been everywhere, then why did it take us so long to see it at all? Let me give you a way to hold the sheer scale of this thing before we go any further, because the numbers involved are so large that they tend to slide off the mind without leaving a mark. A single filament of the cosmic web can stretch for hundreds of millions of light years. A light year is the distance light travels in a year, and light travels fast enough to circle the Earth more than 7 times in a single second. Now imagine that speed sustained for hundreds of millions of years, and that is roughly the length of one strand of the web. Our entire galaxy, the Milky Way, with its hundreds of billions of stars, is about 100,000 light-years across. A single cosmic filament can be thousands of times longer than that. The galaxy you live in is not even a fleck of dust on one strand of this web. It is smaller than that. It is a single bright bead, one of countless beads, strung along a thread so long that the galaxy itself disappears against it. And there is a quiet strangeness in the fact that something so enormous could hide so completely. We're not talking about a faint object at the edge of the observable universe, something so far away that of course we would struggle to see it. We're talking about the structure that is all around us, that we are inside of, that reaches right up to and through our own galaxy. It was not hidden by distance, it was hidden by diffuseness, by the fact that most of the web is made of dark matter that gives off no light at all, and thin gas too faint to register, and that the galaxies which do shine are so widely spaced that, until we mapped enough of them with enough precision, we could not see the pattern they traced. The web hid not in the far distance, but in plain sight, all around us, the way the air hides, or the way the shape of a forest hides from someone standing among the trees, unable to see the wood for them. Part 2. What we only ever simulated. To understand why the cosmic web stayed hidden for so long, you have to understand what we were actually working with for most of the last century. We had a theory. A very good theory, as it turns out, one that has survived test after test, but still a theory, a model of how the universe is put together. It is called the Standard Model of Cosmology, and within that field it goes by a slightly more technical name, lambda cold dark matter, which scientists usually shorten to lambda CDM. You do not need to remember the name. What you need to understand is the picture it paints, because that picture is the foundation of everything we're going to talk about. In this model, the universe is not, at its largest scale, a random soup. It is not a chaotic, formless scattering of matter. Instead, the model says that very early in cosmic history, when the universe was young and hot and almost perfectly smooth, there were tiny ripples in the distribution of matter. Some regions were ever so slightly denser than others, by a fraction of a percent, nothing dramatic. But gravity is patient, and gravity is relentless. Over billions of years, those slightly denser regions pulled in more matter, which made them denser still, which let them pull in even more. The dense regions grew. The empty regions emptied out. And slowly, over the enormous span of cosmic time, the smooth early universe collapsed into the structure we see today. The dense regions became the threads and nodes of the web. The empty regions became the voids. The web was not designed and it was not placed. It grew, the way frost grows across a window, following the cold logic of gravity acting on matter over an almost unimaginable stretch of time. And here is the crucial detail. Most of the matter doing the pulling is not the matter we can see. It is not the stars and the gas and the dust that make up galaxies. The model says that the vast majority of the gravitational scaffolding, the actual skeleton of the web, is made of something we cannot see directly at all, something we call dark matter. Dark matter does not give off light. It does not absorb light. It does not interact with ordinary matter in any way except through gravity. It is, for all practical purposes, invisible. And yet, according to the model, it outweighs all the ordinary visible matter in the universe by a factor of more than 5 to 1. The web you're picturing, that vast glittering spiderweb of galaxies, is really just the visible decoration strung along a much larger, much heavier, completely invisible framework of dark matter. The galaxies are the dew, the dark matter is the silk. Now you can see the problem this creates. If the skeleton of the web is made of something invisible, and if much of the ordinary gas strung along it is too thin and too faint to detect, then how do you ever actually see the web? For most of the history of cosmology you could not. What you could do was simulate it. And this is where the story gets genuinely impressive, because the simulations became extraordinary. Astronomers built enormous computer models, programs that take the laws of physics, the behavior of gravity, the properties of dark matter, the dynamics of gas, and let them run forward across simulated billions of years. The most famous of these is a project called Illustris, and its successor, Illustris TNG. You start the simulation just after the Big Bang, with that nearly smooth early universe, and you let gravity do its work and you watch. And what emerges, every single time, is a web. The same threads, the same nodes, the same voids. The simulated universe arranges itself into a cosmic web that looks startlingly like the patchy, partial glimpses we had managed to catch of the real thing. That was the situation for years. We had a theory that predicted a web. We had simulations that produced a web. And we had scattered, incomplete observations that were consistent with a web. But we did not have the web itself, mapped out clearly, in real data, the way you might map a coastline or a mountain range. We were in the position of someone who has read a detailed description of a city and has seen a beautifully rendered model of that city, and has even caught a few blurry photographs of one or two of its streets, but has never actually stood in the city and looked around. We believed in the web the way you believe in a room you've only ever seen described. We were, in a very real sense, taking it on faith, backed by good math, and belief, even well-founded belief, even belief that turns out to be correct, is not the same as seeing. There is a particular kind of patience required of a scientist, the patience to hold a picture of the universe in your mind for years or decades, supported by indirect evidence, while you wait for the technology that will let you finally check whether the picture is right. For the cosmic web, that wait was long. The web was simply too faint, too diffuse, too spread out across distances too vast for the telescopes we had. We needed an instrument that could do something almost paradoxical. It needed to see the faintest, smallest, most distant galaxies, the ones earlier telescopes had missed entirely, because those faint galaxies are the ones that trace out the true shape of the web. Miss them, and you see only the brightest knots, the equivalent of mapping a city by photographing only its tallest skyscrapers and missing every street and house and alley in between. To see the web, you needed to see the dim things, and then, recently, we built a telescope that could. The lights were about to come on. There is a particular discipline required to live with a theory you cannot yet see confirmed, and astronomers have a long and humbling history with it. Consider that for decades, our entire confidence in the cosmic web rested on an act of trust in mathematics. We trusted that gravity behaves the same way out there, across billions of light years, as it does here in the laboratory. We trusted that the faint ripples we measured in the afterglow of the Big Bang really would grow, over cosmic time, into the structure the equations predicted. We trusted that the invisible dark matter, which we have never held in our hands or caught in any detector, really was out there doing the gravitational work the model assigned to it. None of these were wild guesses. Each rested on solid evidence of its own, but stacked together into a complete picture of a web we could not directly see. They amounted to a remarkable act of collective faith in the power of theory to describe a universe we could only partly observe. And the simulations, for all their beauty, are not the universe. This is a distinction that matters, and serious cosmologists are always careful about it. A simulation takes your assumptions and shows you their consequences. If your assumptions are right, the simulation shows you a true universe. But if your assumptions are subtly wrong, the simulation will faithfully show you the consequences of being wrong, and it will look just as convincing, just as detailed, just as much like a real cosmos. The fact that illustrious TNG produces a beautiful cosmic web does not by itself prove the real universe has one. It proves only that, if our assumptions are correct, there should be one. The simulation is an argument, not a verdict. To get the verdict, you have to leave the computer behind and go look at the actual sky. That is the whole point of what James Webb and the X-ray and radio telescopes finally did. They turned an argument into a verdict. They took a web that existed only in equations and in computer models and in our collective imagination, and they found it, real, out there, written across the depths of time. Part 3. The lights come. On the telescope is the James Webb Space Telescope, and by now you have almost certainly heard of it, because in the few years since it began operating, it has rewritten one corner of astronomy after another. It sits about 1 million miles from Earth, far beyond the Moon, in a cold and stable spot in space where it can keep its enormous golden mirror pointed at the dark without the Earth or the Sun getting in the way. And it sees in infrared light, which is the key to everything we're about to discuss. Infrared is the light of heat, the light of distant and ancient things, the light that has been stretched and reddened by its long journey across an expanding universe. The faintest, most distant galaxies, the ones whose light has been travelling toward us for almost the entire age of the cosmos, glow in infrared. Older telescopes tuned to visible light simply could not see them. James Webb was built precisely to catch that faint infrared glow. It was built to see the dim things, and so a team of astronomers set out to do something that had never been done before. They aimed James Webb at a particular patch of sky, a famous and well-studied region called the Cosmos Field, and they conducted the largest survey the telescope has ever performed. The survey is called Cosmos Webb, and it gathered light from an astonishing number of galaxies, far more than any previous deep survey, including enormous numbers of those faint, low-mass galaxies that earlier instruments had been blind to. Then a researcher named Hussein Hatamnia, working at the University of California, Riverside, led the effort to take all of those galaxies with their carefully measured distances and use them to reconstruct the structure they were arranged on. Not to guess at it, not to simulate it, to map it directly from the real positions of real galaxies. In May of 2026, the result was released to the world. Let me tell you what was in that image, because I want you to feel the weight of it. The map contained roughly 164,000 galaxies. To put that single number in perspective before we go any further, that is more individual galaxies, each one a city of hundreds of billions of stars, than there are minutes in nearly 4 months of continuous time. 164,000 galaxies, each one a Milky Way or larger, each one teeming with worlds, all plotted in their proper places. And when you plot that many galaxies with accurate distances, something remarkable happens. The threads appear, the nodes appear, the voids open up between them. The the cosmic web, the thing we had only ever simulated, resolved into view as real data, traced by the light of 100,000 galaxies. And the map did not just cover the nearby universe. Because James Webb sees so far, and because seeing far means seeing back in time, the map reaches across nearly the entire history of the cosmos. It goes back to a redshift of about 7, which is a way of saying that some of the light in that image left its galaxy when the universe was only a few 100 million years old, an infant compared to its current age of nearly 14 billion years. So the map is not a snapshot, it is a span. It shows the web in the modern nearby universe, and it shows the web as it was when it was young, and it shows everything in between, roughly 13.5 billion years of cosmic structure laid out in a single continuous picture. For the first time, a human being could look at the cosmic web across almost all of time and simply see it. I want you to imagine the moment that image first came together on a screen. Picture the quiet of a research office late in the evening, the soft hum of a computer, the glow of the monitor, the only real light in the room. The data has been gathered, the distance is measured, the calculations run. And now the map renders, point by point, galaxy by galaxy, 164,000 of them arranging themselves into place. And as they fill in, the structure emerges, not a blur, not a guess. Threads of light reaching across the screen, knots where they gather, dark hollows where the voids open up. The person watching is the first human being in history to look directly at the cosmic web spread across the depths of time, to see with their own eyes the structure that organizes everything. There is no fanfare in a moment like that. There is just a person, and a screen, and the slow dawning realization that what they are looking at is not a model of the universe. It is the universe. The thing we had imagined for a century was real, and it was right there, and it had been there all along. That is the feeling I want to carry into the rest of this story, because seeing the web was only the beginning. The map did not just confirm that the web exists. It revealed something about what the web does, a rule written into the data, a rule that turned the cosmic web from a beautiful piece of scenery into something far more active and far more unsettling. The web, it turned out, was not just holding the galaxies, it was shaping them, and to understand how, we have to look closely at the single most important thing that map revealed. It is worth pausing on how the Cosmos Web team actually turned a list of galaxies into a map of the web, because the method is clever, and it tells you something about why this had never been done at this quality before. You cannot simply plot 100,000 dots and call it a map of structure. A galaxy is a point of light, and a point of light by itself tells you nothing about the density of the region it sits in. What the team did instead was a technique called weighted kernel density estimation, which sounds technical but rests on a very intuitive idea. Around every single galaxy, you imagine a soft cloud of influence, denser at the galaxy itself and fading out with distance. Then you add up all those overlapping clouds across all 164,000 galaxies. Where many galaxies sit close together, their clouds pile up and the map glows bright with density. Where galaxies are sparse, the map fades toward dark. Do this carefully, accounting for the distance of every galaxy, and the result is not a scatter of dots, but a smooth, continuous map of how dense the universe is, region by region, across billions of light years. The threads and nodes and voids emerge naturally from the arithmetic of all those overlapping clouds. The reason James Webb could do this when earlier telescopes could not comes down to the faint galaxies. The density map is only as honest as the galaxies it is built from, and if you miss the small, dim, distant galaxies, your map is biased toward the bright ones, which means it is biased toward the densest regions where the big galaxies live. You would see the knots of the web and miss the delicate threads between them, the way a map of a country that showed only its major cities would miss every town and village and country road. James Webb, by catching the faint infrared glow of those small distant galaxies, filled in the towns and the roads. It gave us the threads, not just the knots. And only with the threads can you see the web as a web at all, rather than as a scatter of isolated bright clumps. There is also something poetic and worth dwelling on in what it means that this map reaches back to a redshift of 7. Redshift is the stretching of light by the expansion of the universe, and the further away a galaxy is, the more its light has been stretched on its long journey to us, and the further back in time we are seeing it. A redshift of 7 means we are looking at light that left its galaxy when the universe was only a few 100 million years old, an infant, barely getting started. So when you look at the Cosmos Web map, you are not looking at the web as it is now. You're looking at the web across time, the nearby parts of the map showing the web as it is in the recent universe, and the most distant parts showing the web as it was when it was young and still forming. It is a single image that holds within it nearly the entire history of cosmic structure, from the web's youth to its maturity, all laid out at once. To look at it is to look down the whole length of cosmic time and see the web growing, thickening, organizing itself across the billions of years between the first galaxies and us. Part 4. The Rule. The Map Revealed. When the Cosmos Web team studied their map, they were not just admiring the shape of the web. They were looking for patterns, for relationships, for rules. They wanted to know whether the position of a galaxy within the web had anything to do with the kind of galaxy it was. Was a galaxy sitting in a dense thread different from a galaxy floating alone near the edge of a void? Or were galaxies just galaxies scattered across the web with no connection between where they lived and what they were? And the answer they found is the quiet hinge on which this entire story turns. The answer was that where a galaxy lives is deeply connected to what it becomes. The specific rule they uncovered can be stated very simply, and I want to state it simply first, before we unpack it. The rule is that stellar mass follows density. In plainer words, the more massive galaxies, the giants packed with the most stars, are found inside the densest threads of the web, and the smaller, lower mass galaxies tend to be found in the thinner regions, the sparser strands, the lonelier outskirts. The big galaxies cluster where the web is thick. This is not a small statistical wobble. The correlation holds across cosmic time, at every distance the map could probe, from the nearby universe all the way back toward that infant cosmos at a redshift of 7. Wherever the web is dense, the galaxies grow large. Wherever it is thin, they stay small. Now, why does that matter so much? It matters because it tells us something about cause and effect. If the position of a galaxy in the web were just an accident, if galaxies grew massive or stayed small for reasons that had nothing to do with their surroundings, then you would expect to find big galaxies and small galaxies scattered everywhere, with no relationship to the density of the web around them. But that is not what we see. We see a clear, strong, persistent connection. And the most natural way to explain that connection is that the web itself is feeding the galaxies. The dense threads are where the gas is, where the raw material for building stars piles up, channeled along the filaments by gravity and funneled into the galaxies sitting in those dense regions. A galaxy in a thick strand of the web has a constant supply of fuel flowing into it, so it grows and grows. A galaxy in a thin region runs short of fuel and stays small. The web is not just holding the galaxies in place, it is deciding how much they get to eat. And that single realization breaks the old picture entirely. For a century, the unspoken assumption was that the web was a kind of inert scaffolding, a passive frame that the galaxies happened to be hung upon, like ornaments on a structure that did nothing but support them. The Cosmos Web map says no. The web is not inert. The scaffold is alive. It is moving gas around, feeding some galaxies and not others, and in doing so it is shaping the entire population of galaxies in the universe, sorting them by size according to where they sit. Hold on to that phrase, the scaffold is alive, because we are going to come back to it, and each time we do, it is going to mean something more than it did the time before. Right now, it means the web feeds galaxies. By the time we are finished, it is going to mean a great deal more. There is something almost vertiginous about this when you turn it over in your mind. We tend to think of a galaxy as a self-contained thing, an island universe, complete in itself, doing its own business out there in the dark. But that is not the truth. A galaxy is more like a city built on a river. The river decides whether the city thrives or starves. A city on a great wide river, fed by constant water and trade, grows into a metropolis. A city on a thin and drying stream withers. The galaxy does not choose its river. It does not choose its place in the web. It simply forms where the gas collapses, and from that moment on, its fate is shaped by the strand it happens to sit on. The Milky Way, our own galaxy, the galaxy that made the sun and the earth and ultimately made you, grew massive enough to do all of that because it formed on a strand of the web rich enough to feed it. Sit with that for a moment. Our existence is downstream of the web's geography. We're here because the river was wide enough, but feeding is only half of what the web does to galaxies, and it is the gentler half. Because the same map that showed us how the web nourishes galaxies also showed us something darker. It showed us that the web is involved in how galaxies die, and to understand that, we have to talk about what it actually means for a galaxy to die at all. I want to slow down on the mechanism here, on how exactly the web feeds the galaxies in its dense strands, because the picture is genuinely beautiful once you see it clearly. Gas does not just sit randomly in space. It flows, pulled by gravity, and the filaments of the cosmic web are the channels along which it flows. Think of the web as a vast system of rivers, with the gas as the water. The filaments are the riverbeds, and gravity is the slope that makes the water run downhill, always toward the denser regions, always toward the nodes where the great clusters sit. A galaxy that forms in a dense thread of the web is like a settlement built where two rivers meet. It has gas flowing into it constantly, fresh fuel delivered along the filaments, and so it can keep making stars, keep growing, keep building itself into a giant. A galaxy in a thin region, far from the main channels, gets only a trickle and stays small. This flowing gas even has a name in cosmology. Astronomers talk about cold accretion, the process by which cold gas streams along the filaments directly into galaxies, feeding their star formation. For a long time this was mostly theoretical, a process seen clearly in simulations but hard to catch in the act in the real universe. The Cosmos Web Map does not show us the individual streams of gas, but it shows us their consequence written across 100,000 galaxies at once. The fact that the most massive galaxies reliably sit in the densest regions is exactly what you would expect if the web has been feeding them along its filaments for billions of years. The map is the fingerprint of all that flowing gas, all those cosmic rivers, recorded in the distribution of galaxy mass. And there is a subtlety in the data that is worth drawing out, because it shows how careful this kind of science has to be. The relationship between a galaxy's environment and whether it is still forming stars was not simple and fixed. It changed across cosmic time, and it depended on the kind of galaxy. For the galaxies that had already stopped forming stars, the quiet ones, the connection to density was one way in the recent universe and reversed further back in time. For the galaxies still actively making stars, the relationship was different again. This is not a flaw in the finding. It is the opposite. It is the kind of rich, detailed, time-dependent behavior that tells you the web is genuinely interacting with galaxies in complex ways, not just sorting them by a single simple rule. The headline, that stellar mass follows density, is real and strong. But underneath it lies a whole layer of detail about how that relationship shifted as the universe aged, as the web matured, as the dominant forces shaping galaxies changed over the long course of cosmic history. The web's influence on galaxies is not one thing. It is a story that evolved. When you hold all of that together, the old picture of the inert scaffold does not just bend, it collapses entirely. You cannot look at 100,000 galaxies sorted by the density of the web around them, fed along cosmic rivers of gas in ways that changed and evolved across the entire history of the universe, and still believe the web is just a passive frame. The web is a participant. It always was. We simply could not see the evidence until we could map the web itself. Part 5. How Galaxies Die. A galaxy does not die the way a star dies. There is no single moment, no explosion, no flash that marks the end. A galaxy dies slowly, and quietly, and the death has a specific meaning that I want to be precise about. When astronomers say a galaxy has died, they mean it has stopped forming new stars. A living galaxy is one that is still making stars, still collapsing clouds of cold gas into fresh suns, still lighting new fires in the dark. A dead galaxy is one that has run out of the ability to do that. It still has its old stars, the ones it made long ago, and those stars go on shining for billions of years, slowly reddening and fading. But no new stars are being born. The fires are all old fires now, and one by one, over the long ages, they will burn out, with nothing to replace them. The galaxy becomes a kind of slow sunset, beautiful and fading, with no new dawn coming. Astronomers call this quenching. A quenched galaxy is a galaxy whose star formation has been shut off. The deep question, the one cosmologists have argued about for a long time, is what does the quenching? What is it that reaches into a galaxy and shuts off its ability to make stars? And here the Cosmos Web map revealed something genuinely surprising, something that complicates the whole picture in a fascinating way. It turns out that the answer changed over time. The thing that kills galaxies in the early universe is not the same as the thing that kills galaxies in the later universe. The universe, in effect, changed its murder weapon partway through its history. In the early universe, going back past a redshift of about 2.5, which is to say more than 11 billion years ago, galaxies mostly died from the inside. The killer was internal. Deep in the heart of many galaxies sits a supermassive black hole, a monster millions or billions of times the mass of the Sun, and when that black hole is feeding, when gas is spiraling into it, it does not swallow that gas quietly. It blazes. The region around a feeding supermassive black hole becomes one of the most luminous and violent places in the universe, pouring out radiation and driving enormous winds of energy outward through the galaxy. And those winds can be so powerful that they heat the galaxy's gas, or blow it out entirely, or simply stir it up so violently that it can no longer collapse to form stars. The galaxy strangles itself from within. The very black hole at its centre, the heart of the galaxy, becomes the thing that shuts it down. In the early universe, this internal process, this self-inflicted death by black hole, was the dominant way galaxies quenched. But as the universe aged, something shifted. The web grew. Over billions of years, gravity pulled the threads of the web tighter, made the dense regions denser, built up the great clusters where thousands of galaxies crowd together, and as those dense environments matured, they became deadly in their own right. By the later universe, for smaller galaxies especially, the dominant killer was no longer the black hole within, it was the web without. The environment itself had become the murderer. A small galaxy drifting through the cosmos would fall into one of these dense regions, one of these thick knots of the web, and the moment it did, its gas would begin to be stripped away. Pulled out of it by the pressure of the dense surroundings, torn loose by the gravity of all the matter packed around it, the galaxy's reservoir of star-making fuel would simply be removed. And without that gas, the galaxy could not form stars. It was quenched, not by anything it did, but by where it ended up. The web killed it. I want you to feel the weight of that, because this is the first place in our story where the science becomes something more than science. Think about what this actually means for a galaxy. In the early universe, a galaxy that died at least died by its own hand, strangled by its own central engine, its fate sealed by something it carried inside itself. But in the later universe, a galaxy can be killed simply for being in the wrong place. A small galaxy, full of gas, full of the potential to make billions of new stars and light up countless new worlds, drifts a little too close to a dense thread of the web, and the web reaches out and strips it bare. Not because there was anything wrong with the galaxy, not because it had exhausted itself, simply because it wandered into a region where the environment does not allow life to continue. Its star-making future, all those uncreated suns, all those uncreated worlds gone, stripped away by an accident of location. A galaxy is not the master of its own fate. That is the realization that lands here, and it is a heavy one. We like to imagine that things rise and fall according to what they are, according to some internal quality, some merit or flaw they carry within them. But the universe at its largest scale does not work that way. A galaxy that falls into the wrong part of the web has its gas stripped and never makes another star, no matter how much gas it had, no matter how many stars it might have made, no matter what it might have become. Survival, for a galaxy, is partly just an accident of where it happens to be standing when the dense regions of the web close around it. The web giveth, feeding the galaxies in its rich strands, and the web taketh away, starving the ones that fall into its deadly knots. And none of the galaxies get a say in which fate is theirs. That is what the optical map revealed. The great picture painted in infrared light by the largest survey James Webb has ever done, but it was only the first of our 5 discoveries, and in some ways the gentlest. Because the next telescope to turn its gaze on the Webb was not looking in infrared at all. It was looking in X-rays, the light of the hottest and most violent things in the universe. And what it found solved a mystery that had haunted cosmology for decades. A mystery about something far stranger than dead galaxies. It was a mystery about where half of the universe had been hiding. There is a detail in the timing of all this that deserves a closer look, because it reveals something profound about how the universe itself has changed over its lifetime. The shift from internal quenching to environmental quenching, from galaxies dying by their own black holes to galaxies dying by the Webb, was not arbitrary. It happened because the Webb itself grew up. In the early universe, the Webb was young. Its threads were thinner, its dense regions less dense, its great clusters not yet assembled. There simply were not many places dense enough to strip a galaxy of its gas by environment alone. So in that early era, if a galaxy was going to die, it mostly had to do it to itself, from the inside, through the violence of its own central black hole. The environment was not yet deadly enough to do the job, but the Webb is patient, like gravity, and over billions of years it thickened. The dense regions grew denser. The clusters assembled, packing thousands of galaxies into crowded, gas-filled, gravitationally violent environments. And once those environments existed, they became a new and powerful way for galaxies to die. A galaxy no longer had to strangle itself. It could simply fall into one of these mature, dense regions and have its gas stripped away by the environment. So the change in how galaxies die is really a record of the Webb growing up. The murder weapon changed because the universe changed, because the Webb matured from a thin young framework into a thick and deadly structure, capable of killing galaxies just by pulling them into its dense knots. The history of galaxy death is, in a strange way, a biography of the cosmic web itself, a record of it growing strong enough to do what it could not do when it was young. And I keep coming back to what this means for the individual galaxy, for the specific small galaxy that finds itself falling toward a dense region of the web, because there is a real poignancy in it that the statistics can hide. Imagine a small galaxy, full of cold gas, full of the potential to make billions of new stars over the coming eons. Left alone, in a quiet region of the web, it would go on making stars for a very long time, lighting new suns, perhaps warming new worlds, perhaps, who knows, eventually cradling new life on some planet circling some star it has not yet made. But it drifts, slowly, pulled by gravity, toward a dense thread, toward a cluster. And as it falls in, the stripping begins. Its gas is pulled away. Its future, all those uncreated stars and uncreated worlds, is removed from it, drawn off into the surrounding space. The galaxy does not get a say. It did nothing wrong. It simply formed in a place and drifted in a direction, and that direction led into a region of the web where life, for a galaxy, is no longer possible. Its fate was written by geography, by the accident of where it sat in the web, and by the slow blind pull of gravity drawing it toward its end. We do not usually think of the universe as a place where location is destiny. We like to imagine that what happens to a thing depends on what the thing is, on some quality it carries inside itself. But the cosmic web does not work that way. For a galaxy, Much of destiny is simply a matter of address, of which strand of the web you happen to occupy, of whether the slow drift of gravity is carrying you toward a rich feeding ground or toward a dense and deadly knot. The web feeds, and the web starves, and the galaxies caught in it do not choose which fate is theirs. Part 6. The half of the universe that went missing. There is a problem in cosmology that is old enough and strange enough that I need to set it up carefully, because when you first hear it, it sounds like a mistake, like someone simply lost track of their arithmetic. The problem is this. For decades, when astronomers added up all the ordinary matter in the universe, all the normal stuff, the protons and the neutrons and the electrons, the atoms that make up stars and planets and gas clouds and people, they kept coming up short. Roughly half of it was missing. Not slightly off. Not a rounding error. Fully half of the ordinary matter that should exist could not be found. Now, I need to be very clear about what kind of matter we're talking about, because this is easy to confuse, and the confusion would ruin the whole point. We're not talking about dark matter here. Dark matter is its own separate mystery, that invisible gravitational scaffolding we discussed earlier, and nobody expected to be able to see that directly anyway. No, the missing matter in this problem is ordinary matter, the same kind of matter that you are made of, the same kind of matter in the air you're breathing and the chair you're sitting in. Astronomers call it baryonic matter, after the protons and neutrons that make it up, but you can just think of it as normal stuff. And the puzzle was that when they counted up all the normal stuff they could actually see, in galaxies and gas clouds and everything else, it came to only about half of what their calculations said should be there. How do you even know something is missing if you cannot see it? It comes down to a comparison between two very different ways of counting. On one side, you have the early universe. By studying the faint afterglow of the Big Bang, the radiation left over from when the cosmos was young and hot, cosmologists can calculate with great precision exactly how much ordinary matter the universe started with. The numbers there are solid, tested, reliable. On the other side, you have the present-day universe, where you try to add up all the ordinary matter you can actually detect, all the matter locked in stars and galaxies and the visible clouds of gas between them. And when you compare the two numbers, the amount the universe started with versus the amount we can find now, there is a gap. About half of the ordinary matter that should be here, somewhere, is not showing up in any of the places we know how to look. The matter did not vanish. Matter cannot simply vanish. It had to be somewhere. But where? The leading suspicion for years was that the missing matter was hiding in the cosmic web. The simulation suggested that a great deal of ordinary matter should exist as thin, diffuse gas strung along the filaments of the web in the vast spaces between the galaxies. Not in the galaxies, between them. This hypothetical gas even had a name, the warm-hot intergalactic medium, which scientists abbreviate as the WHIM. The idea was that the missing baryons were out there in the WHIM, in the threads of the web spread so thin and so faint that we simply could not detect them. But suspecting something and proving it are very different things. For years, the WHIM was a prediction, an expected hiding place, but the gas itself remained stubbornly invisible. It was too diffuse to glow in ordinary light. To find it, you would need to catch it by some other means. You would need to catch it by its heat, and in late 2025 that is exactly what happened. A team of astronomers, using two X-ray telescopes, Japan's Suzaku and Europe's XMM Newton, turned their attention to a particular region of the cosmos, a place called the Shapley supercluster. The Shapley supercluster is one of the most massive concentrations of galaxies in the relatively nearby universe, sitting about 650 million light-years away in the direction of the constellation Centaurus. It is a place where the cosmic web bunches up dramatically, where several of its tendrils come together, and running between 4 of its galaxy clusters, the team found something extraordinary. A filament, a single thread of the cosmic web stretching across roughly 23 million light-years, connecting cluster to cluster like a bridge spanning a chasm. Let me give you that distance in a way you can actually hold. 23 million light years. Our entire Milky Way galaxy, edge to edge, is about 100,000 light years across. So this single filament, this one strand of the web, is more than 200 Milky Ways laid end to end. A bridge of gas more than 200 galaxies long. And the reason we had never seen it before is that the gas in it is spread unimaginably thin. There are only about 10 particles in every cubic meter of it. To call that a vacuum is an understatement. The best vacuum we can make in a laboratory on Earth is denser than this. And yet, against that near-perfect emptiness, the gas in this filament is searingly, violently hot. More than 10 million degrees Celsius. The few particles that are there are screaming with heat. And it was that heat, that faint X-ray glow given off by gas at 10 million degrees, that finally gave the filament away. The gas was too thin to see in ordinary light, but it was too hot to hide in X-rays. I want you to come out there with me for a moment, into that gap between the four clusters, because it is one of the strangest places in this entire story. Imagine you're drifting in the middle of this filament, suspended in what looks, to your eyes, like perfect and absolute emptiness. There are no stars near you. There are no planets, no clouds, nothing you could see or touch. By every visual sense you have, you're floating in a void, in the most complete nothingness imaginable. And yet the space around you is not empty, and it is not cold. It is a furnace. The few scattered particles drifting past you carry the temperature of the inside of a stellar explosion, more than 10 million degrees, hotter than the core of many stars. You cannot see this heat. You cannot feel it the way you would feel the warmth of a fire, because the gas is too thin to transfer much heat to you directly. But it is there, glowing faintly in X-rays, a light your eyes were never built to see. You would be floating in what seems like the emptiest place in existence, and you would be wrong. You would be floating inside one of the great hidden reservoirs of the universe, in a thread of fire stretched across 23 million light years of dark. And here is the part that should make the back of your neck prickle. Half of all the ordinary matter in the cosmos lives in places exactly like this, because that is what this filament proved. When the team measured the total mass of hot gas in that single thread, it came to roughly 12 trillion times the mass of the Sun, about 10 times the entire mass of the Milky Way, in just one filament, in the form of gas so diffuse we had never been able to detect it. And it matched. It matched the predictions of the simulations, matched the expected properties of the warm, hot intergalactic medium, matched the missing baryons we'd been hunting for decades. The missing half of the ordinary universe was not lost. It was never lost. It was hiding exactly where the web said it would be, strung along the filaments, between the galaxies, too thin to see and too hot to fully hide. And that realization should reorganize your entire mental picture of the cosmos. The galaxies, all those bright cities of stars, are not where most of the ordinary matter is. Most of the ordinary matter, the same kind of matter in your blood and your bones, has never lived inside a galaxy at all. It has been drifting in the dark threads between the galaxies since before the Sun existed. A vast and invisible ocean, with the galaxies as nothing more than the rare bright islands rising out of it. Remember the city we talked about earlier, the one we could only see by its lights. We mapped the universe the way you would map a city by photographing only its lit windows at night, and we thought the windows were the city. But the X-ray filament shows us the streets between the windows, the dark spaces we had ignored, and it turns out that is where most of the city actually is. The lights were never the whole story. They were barely half of it. The real structure was always in the dark. So now we have 2 of our 5 discoveries. The infrared map showed us the web feeding and starving galaxies, shaping their lives and deaths. The X-ray filament showed us that the web is where most of the ordinary universe has been hiding all along. But so far in both of these, the web has been a static thing, a structure that feeds, a structure that hides matter, but a structure that, in our picture, has been sitting still. The next discovery shattered that, because when astronomers listened to the web in radio waves, they did not find something sitting still. They found something moving. They found something spinning. It is worth understanding just how the astronomers managed to pull this faint signal out of an enormously complicated piece of sky, because the technique is a small masterpiece of careful observation. The problem with looking for faint diffuse gas in X-rays is that the sky is full of bright X-ray sources that can drown it out. Scattered throughout the filament and the clusters it connects are supermassive black holes, feeding and blazing, pouring out X-rays far brighter than the faint glow of the diffuse gas. If you just pointed a telescope at the region and added up all the X-rays, those bright black holes would swamp everything, and the gentle glow of the filament would be lost in their glare. So the team used 2 telescopes in tandem, each doing what it does best. The Japanese telescope, Suzaku, was good at mapping faint X-ray light spread across a wide region, so it provided the broad picture of the glow, and the European telescope, XMM Newton, with its sharper vision, zoomed in to precisely locate each of those bright contaminating black holes so they could be identified and subtracted out, removed from the data, leaving behind only the faint diffuse glow of the gas itself. It was a kind of cosmic noise cancellation, carefully erasing the bright interlopers to reveal the quiet structure underneath. And the density of this gas is worth dwelling on, because it is so far outside ordinary intuition. The filament gas is denser than the average emptiness of intergalactic space, about 30 to 40 times denser than the cosmic average. And yet, in absolute terms, it is still almost nothing at all, around 10 particles per cubic meter. Hold those 2 facts together, because the combination is what makes the missing matter so hard to find. The gas is dense by the standards of intergalactic space, which is why it traces the filament, why it marks out the structure of the web, but it is so thin by any human standard that it makes the best laboratory vacuum on Earth look crowded by comparison. This is matter that is simultaneously concentrated, relative to the void, and almost unimaginably diffuse, relative to anything we know. That is exactly why it stayed hidden for so long. It is concentrated enough to hold a vast amount of mass when you add up its enormous volume, and diffuse enough that, point for point, it is nearly undetectable. The missing matter was not hidden in some exotic form or some unreachable place. It was hidden in plain sight, in the sheer diffuseness of gas spread across millions of light years. When you multiply that thin gas across the staggering volume of a 23 million light-year filament, the total comes to roughly 12 trillion times the mass of the Sun. That is the resolution to a problem that haunted cosmology for decades, sitting right there in a single thread of the web, and it is almost certainly not unique. This is one filament in one supercluster that happened to be close enough and oriented well enough for us to detect. The web is full of filaments. If this one holds 12 trillion solar masses of hidden hot gas, then the web as a whole holds an ocean of it, the missing half of the ordinary universe, distributed through the threads between the galaxies, exactly where the simulations always said it would be. The detection of this one filament is a window onto a truth about the whole cosmos. Most of the ordinary matter in the universe is not in the galaxies at all. It is out there, in the dark, in the diffuse hot threads of the web, and it always has been. Part 7. The Web in Motion. To listen to the universe in radio waves is to hear a different story than the one you see in visible light. Radio astronomy picks up things that are invisible to the eye, and one of the most important is a particular signal given off by clouds of cold hydrogen gas, the raw material from which stars and galaxies are made. By tuning enormous radio telescopes to this signal, astronomers can map where the cold gas is, and crucially they can measure how it is moving. Because the radio signal shifts very slightly depending on whether the gas is coming toward you or moving away, listening to hydrogen lets you measure motion across the cosmos with extraordinary precision. And motion, it turns out, is where the next chapter of our story lives. A team of astronomers used a survey called MIGHTY, conducted with a magnificent radio telescope in South Africa called Meerkat, an array of 64 linked dishes working together as a single instrument. They were studying a stretch of the cosmic web, looking at the cold hydrogen gas in the galaxies strung along one particular filament, and they combined their radio observations with optical measurements from other instruments to pin down exactly where each galaxy sat and exactly how it was moving. What they found, when they put it all together, was a filament containing 14 galaxies, all rich in hydrogen, arranged in a long, thin line. The core of this structure measured about 5.5 million light-years from end to end, and the full rotating filament reaches across something closer to 50 million light-years, a thread of 14 galaxies stretched across tens of millions of light-years of space. And here is what made it remarkable. The galaxies were not just sitting in the filament, they were orbiting around its spine. The entire structure was turning. The filament was not a static thread, not a still line of galaxies hanging motionless in space. It was rotating, like an impossibly long, impossibly slow cylinder, with the galaxies wheeling around its central axis. This is one of the largest rotating structures ever discovered in the universe. Think about what that means physically. We're used to things spinning at human scales, a top, a wheel, a planet. We are used to galaxies spinning, vast as they are. But here is a structure tens of millions of light-years long, containing 14 entire galaxies, and the whole thing is turning, slowly, majestically, on an axis that runs down its length. The web does not just sit there. The web spins, and the discovery went deeper than just noticing the rotation. The astronomers found evidence that the filament was handing its spin to the galaxies inside it. Angular momentum, the physical quantity that describes rotation, was being transferred from the great turning thread to the individual galaxies caught up in it. The filament was, in a sense, teaching the galaxies how to spin. And this opens up a genuinely profound possibility, one that reaches all the way down to the galaxy you live in. Because every spiral galaxy spins. The Milky Way spins. The Sun, carrying the Earth with it, sweeps around the centre of our galaxy once every 200 and some million years, riding the great rotation of the galactic disk. We have long wondered where that spin comes from. Why does a galaxy rotate at all? Why is there a flat spinning disk in the first place, rather than just a formless cloud of stars? This filament offers a piece of the answer, and it is a beautiful one. The spin of a galaxy may be inherited. It may be handed down from the larger structure the galaxy formed in or fell into, passed from the turning filament to the galaxy, the way a parent's traits are passed to a child. When a galaxy condenses out of the gas flowing along a filament, or when it tumbles into a filament from outside, it may pick up its rotation from the great slow turning of the web itself. The reason the Milky Way turns, the reason there is a flat disk for the Sun to orbit within, the reason our night sky has the shape it has, may be a rotation that was set in motion by a thread of the cosmic web older than the galaxy itself. Our galaxy may have learned to spin from the web, the way the 14 galaxies in that distant filament are visibly learning to spin right now. The scaffold is alive. We keep returning to that phrase, and look at how much heavier it has become. When we first said it, back when we were talking about the infrared map, it meant only that the web feeds galaxies, channeling gas into the ones sitting in its dense strands. Now it means something far more literal. The scaffold moves. The scaffold turns. The scaffold reaches into the galaxies caught within it and sets them spinning, hands them the very rotation that defines their shape. This is not the behavior of inert scenery. This is the behavior of something dynamic, something active, something that participates in the lives of galaxies at the most fundamental level. The web is not where galaxies happen to be. The web is part of what galaxies are. But spinning is, in its way, a gentle thing. A filament handing a galaxy its rotation is almost a gift, a kind of cosmic inheritance. The next discovery is not gentle at all. Because the same kind of radio observation that revealed the spinning filament also caught the web doing something violent, something that we usually only get to talk about as a thing that happened in the distant past. This time, astronomers caught the web in the act of killing a galaxy, right now, in real time, and they watched it pull the galaxy apart in a stream of gas more than 1 million light-years long. To appreciate why a spinning filament is so surprising, It helps to remember how we used to think about where galaxies get their spin in the first place. The traditional picture, worked out long ago, held that galaxies acquire their rotation through a process of gentle gravitational torquing in the early universe. As structures were first collapsing, neighbouring clumps of matter would tug on each other, and the slight off-centre nature of those tugs would impart a small twist, a bit of angular momentum to each forming galaxy. In that picture, spin is something a galaxy gets early and locally, from the tidal tugs of its immediate neighbours during its formation. It was a sensible idea, and it captured part of the truth, but it treated the larger web mostly as a backdrop, a static framework within which these local interactions played out. The web set the stage, but the spin came from the actors, not the stage itself. The discovery of a rotating filament complicates that tidy story in the most interesting way. It suggests that the web is not merely the stage on which galaxies acquire spin through local tugs. The web itself carries angular momentum on the grandest scale, and it can pass that rotation down to the galaxies within it. The spin of a galaxy may not be purely a local inheritance from its immediate neighbours. It may be, at least in part, a gift from the entire filament, a portion of the great slow rotation of a structure tens of millions of light-years long. This reframes the origin of galactic spin from something small and local to something vast and structural. The reason a galaxy turns may be written not just in its immediate surroundings at birth, but in the rotation of the cosmic thread it belongs to, a thread far older and far larger than the galaxy itself. And the detail that the astronomers actually caught angular momentum being transferred from the filament to the galaxies within it is what makes this more than a curiosity. It is one thing to find a large structure that happens to be rotating. It is another to find evidence that the rotation is flowing from the structure into its galaxies, that the web is actively spinning up the galaxies caught in it. That is the difference between a coincidence and a mechanism. The filament is not just spinning near these galaxies, it is, in a real sense, teaching them to spin, handing each one a share of its own great rotation. And if that process is common, if filaments across the universe routinely pass their spin down to the galaxies within them, then the rotation of nearly every spiral galaxy, the great wheeling disks that fill the cosmos, may carry within it an echo of the turning of the web. The Milky Way's spin, the rotation that gives our night sky its shape and carries the sun in its long orbit, may be in part a rotation inherited from a thread of the cosmic web that was turning before our galaxy was fully formed. Part 8. A galaxy. Being starved, right now. Earlier, when we talked about how galaxies die, we discussed the process in the abstract. We said that in the later universe, the web kills galaxies by stripping away their gas as they fall into dense regions, and that without gas, a galaxy can no longer form stars. That was the theory, drawn from the great statistical patterns in the infrared map. But there is a difference between knowing that something happens in general and actually watching it happen to a specific victim. And in 2025, astronomers got to watch. They caught a galaxy, or rather a pair of galaxies, in the very act of being stripped, and the scale of what they saw is hard to fully absorb. The discovery was made with a radio telescope in Australia called ASCAP, as part of a survey of cold hydrogen gas. The astronomers were looking at two small galaxies, dwarf galaxies, named NGC 4532 and DDO 137, sitting about 53 million light-years away, near the Great Virgo cluster of galaxies. And between these two dwarf galaxies, they found a bridge of neutral hydrogen gas, stretching across 185,000 light-years, connecting the two galaxies like a rope of gas thrown between two ships. To give you a sense of that scale, 185,000 light-years is nearly twice the width of the entire Milky Way's disk. The bridge of gas between these two small galaxies is larger than our whole galaxy. But the bridge was only the beginning. Trailing behind the pair, streaming away from them into space, was a tail of gas extending 1.6 million light-years. A tail more than 1.5 million light-years long. This is the longest such tail ever observed, anywhere in the universe. And when the astronomers worked out what was happening, The picture they assembled was both clear and quietly devastating. The two dwarf galaxies are orbiting each other, locked in a slow gravitational dance, and together they are falling toward the Virgo cluster. The Virgo cluster, like all great clusters, is surrounded by an enormous halo of hot gas heated to something like 200 times the temperature of the Sun's surface. And as the two dwarf galaxies plunge into this hot halo, into this dense region of the web, they experience something called ram pressure. Ram pressure is exactly what it sounds like. Imagine running through water or sticking your hand out the window of a moving car. The faster you move through a medium, the more it pushes back against you. As the two galaxies fall through the hot, dense gas surrounding Virgo, that gas pushes back against the cold gas inside them, and it strips it away. The galaxy's own star-making fuel is torn out of them, pulled loose by the pressure of their fall, and tidal forces from the gravitational interaction stretch and pull at the gas as well, drawing it out into that immense bridge and that record-breaking tail. The galaxies are being plucked clean. Their gas, the raw material for every star they might ever make, is being pulled out of them and strung across millions of light-years of space. And this is not ancient history. This is not something that happened billions of years ago that we're seeing in old light. By cosmic standards, this is happening now. We have caught the web in the act. I want to take you somewhere for this one. I want you to stand on a world inside one of these doomed galaxies and feel what this looks like from the inside, because the view from within is where the real weight of it lives. Imagine you're standing on a planet circling a star somewhere in NGC 4532, one of these two falling dwarfs. Above you is a night sky, and it is full of stars, the familiar glittering canopy of a living galaxy. Your galaxy is still alive. It is still making new suns. The sky still gains new lights, slowly, over the long ages. But something is wrong. Something you could measure if you watched long enough across the generations. The gas is thinning. The great clouds from which new stars are born are being pulled away, drawn off into a stream that reaches out beyond your galaxy and into the dark. A stream more than 1 million light-years long, far longer than your entire galaxy. And as that gas leaves, the births slow. Fewer new stars each 1,000,000 years, then fewer still. You're standing inside a galaxy that is being slowly, gently, irreversibly starved. There is no violence you could see in your sky, no explosion, no catastrophe, just a slow, quiet thinning, the gas being drawn away thread by thread, until one distant day there will be nothing left to make new stars from, and the last new sun in your galaxy will be born, and after it, no more, ever. This is what the death of a galaxy looks like from the inside, not a bang. A long, slow, beautiful fading as the web pulls the future out of you a little at a time. That is the hardest thing in this story, I think. Because we have all heard about the dramatic deaths in the universe, the supernova, the colliding black holes, the violent and sudden ends. But this is a different kind of death entirely. This is death by starvation, death by simple proximity to a dense region of the web, death so slow and so quiet that from inside the dying galaxy you would barely be able to tell it was happening at all. And it is the web doing it. The same web that feeds galaxies in its rich strands reaches out here and starves these two. The scaffold is alive, and it does not only build, it also takes apart. It strips, it starves, it kills, slowly, and at a scale that turns a whole galaxy's worth of star-making future into a fading stream of gas drifting off into the dark. And now we have to bring this home. Because so far, every galaxy we have talked about, the ones being fed, the ones being starved, the ones being spun, has been a distant stranger, millions or billions of light years away. It is easy to hold a stranger's death at arm's length. But the next discovery does not let us do that. The next discovery reaches all the way to our own galaxy, the Milky Way, the one we live in, and shows us the web's fingerprint pressed into its very shape. There is a name for the kind of feature that streams off these falling galaxies, and it connects this real-time death to a whole family of strange shapes we see across the universe. When a galaxy has its gas and stars pulled out into a long trailing stream by gravitational and pressure forces, astronomers call the result a tidal tail. You have very likely seen images of tidal tails without knowing the name, those striking pictures of galaxies with long, graceful streamers of stars and gas curling away from them, like a comet the size of a galaxy. The famous Tadpole galaxy is one example, trailing an enormous tail of stars drawn out by a past encounter. These tails are the visible scars of gravitational violence, the marks left when one structure pulls material out of another, and the tail trailing off the two Virgo dwarf galaxies at 1.6 million light-years is the longest such tail ever recorded. It is a tidal tail on a scale that dwarfs almost anything else we have seen. A stream of stripped gas longer than 15 Milky Ways laid end to end, drawn out of two small galaxies by their fall into the web. What makes this particular case so valuable to astronomers is that it lets us watch a process we usually can only infer. Most of the time, when we talk about galaxies being stripped of their gas, we are talking statistically, reconstructing what must have happened from the populations of dead galaxies we find in dense regions. We see the corpses and deduce the cause of death. But here, with these two dwarf galaxies, we have caught a living galaxy in the very act of dying, mid-process, with its gas visibly streaming away into space. It is the difference between studying death from autopsy reports and witnessing it directly. We can see the bridge of gas between the two galaxies, see the immense tail trailing behind, see the geometry of the fall toward the Virgo cluster, and from all of that reconstruct in real time exactly how the web reaches into a galaxy and pulls the future out of it. This is the mechanism of environmental quenching, not as a theory, but as an event we are watching unfold. And the slowness of it is part of what makes it so haunting. From our perspective, with our brief human lives, the process looks frozen, a single still image of gas suspended in space. But it is not frozen. It is happening on the vast slow clock of cosmic time over hundreds of millions of years. From inside the galaxy, as we imagined a moment ago, there would be no drama, no visible catastrophe, just the slow generational thinning of the gas, the gradual decline in the birth of new stars, a sky that very slowly stops gaining new lights. A civilization living through it, if there were one, might take a very long time to even notice that anything was wrong, that their galaxy was being quietly emptied of its future. By the time the loss became obvious, it would already be far along. There is something almost merciful in that slowness, and something almost unbearably sad. The galaxy is being killed so gently that it would hardly feel the blow, even as everything it might have become is drawn away into the dark, one thread of gas at a time. Part 9. The Webb's Fingerprint. In our own galaxy. We tend to picture galaxies as flat. When you see an artist's rendering of a spiral galaxy, or a photograph of one seen face on, it looks like a perfect disk, a great flat pinwheel of stars, smooth and even as a dinner plate. And for a long time, that was roughly how we imagined our own galaxy too, the Milky Way as a flat spinning disk with the sun sitting somewhere out toward the edge. But that picture is not quite right. Real galaxies, including ours, are often not flat at all. Many of them are warped. The disk is bent, twisted out of the plane so that the edges curl up on one side and down on the other. Picture a vinyl record left too long in the sun, sagging and curling at its edges, no longer a perfect flat plane but a gentle warped curve. That is what many disk galaxies actually look like, and that is what our Milky Way looks like too. We know this for certain about our own galaxy, and we know it thanks to one of the most remarkable instruments ever flown, the Gaia Space Telescope. Gaia's mission was to measure the positions and motions of more than 1 billion stars in our galaxy with staggering precision, building the most detailed three-dimensional map of the Milky Way ever made. And when astronomers studied that map, they found that the stars in the outer regions of our galaxy are not moving the way they would if the disk were flat. There are subtle deviations, slight wobbles in the motions of stars in different parts of the galaxy, and those deviations trace out a warp. The Milky Way's disk is bent. One side rises above the central plane, the other dips below it, and the whole warp itself slowly precesses, wobbling around over time like a spinning top that is not quite balanced. Other tracers, like a class of pulsating stars called RR Lyrae stars, confirm the same thing. Our galaxy is warped, and there is no longer any doubt about it. For a while, the warp was just a curiosity, an odd feature of our galaxy and many others, with no obvious explanation. But in late 2025, a study led by a researcher named Wenbei Zi took a careful look at hundreds of warped galaxies and asked a question nobody had quite answered before. Is the warp random, or is there a pattern to it, some hidden order in the way galaxies are bent? And the answer they found connects the shape of galaxies directly to the cosmic web. The study discovered that the warp is not random at all. The way a galaxy is bent, the direction and character of its wobble, is tied to its alignment with the nearest filament of the cosmic web. Galaxies that sit inside rich, dense, enriched filaments, the thick strands full of matter, are far more likely to be warped and distorted. Galaxies that float in relative isolation, away from the dense threads, tend to stay flat and undisturbed. Think about what that means. It means the gravitational tidal forces of the larger web, the pull of all that matter strung along the filaments, are physically bending the shapes of the galaxies that live inside it. The web does not only feed galaxies, and starve them, and spin them, it also reaches out and bends them, warps their disks, presses its influence into their very form. A galaxy in a dense strand of the web is like a sapling growing in a strong and steady wind. It does not grow straight. It grows bent, shaped by the force pressing on it, carrying the mark of that force in its form for as long as it lives, and the warp of a galaxy is exactly that kind of mark. It is the shape the web has pressed into the galaxy, and here is where it stops being abstract. Here is where it comes home. The Milky Way is warped. Our galaxy carries this mark. The same kind of tidal forces that bend strangers 13 billion light-years away, the same web that we have been watching feed and starve and spin distant galaxies through this entire story, has reached into our own galaxy and bent it. This is not a distant galaxy we're talking about anymore. This is the Milky Way, the galaxy the sun rides inside, the galaxy that made the Earth, the galaxy you live in right now, and it is bent, warped, shaped by the hand of the cosmic web. When you look up at the band of the Milky Way arching across a dark night sky, you are looking at a structure that has been physically reshaped by the largest structure in the universe. The web's fingerprint is right there, pressed into the galaxy over your head. We said at the very beginning that we were standing inside the largest structure in the universe the whole time, and blind to it. Look at how that phrase has changed. When we first said it, it was almost an abstraction, a fact about ignorance, a statement that the web was big and we had not noticed it. But the Milky Way's warp turns it into something else entirely. It proves that we were never merely observers of the web, looking at it from some safe distance outside. We were always residents of it. We live inside one of its strands. We were shaped by it. The galaxy we live in is bent by it. We did not stumble upon the web as outside explorers finding a new continent. We woke up finally to the structure we had been living inside all along, the structure that had already pressed its shape into our home before we even knew it was there. We were standing inside it the whole time, and now we can see the proof of it written into the shape of our own sky. So now we have all 5 of our discoveries, 5 separate observations, 5 separate ways the web reaches into the lives of galaxies. The infrared map that showed us the web feeding the galaxies in its dense strands and starving the ones that fall into its deadly knots. The X-ray filament that revealed the web as the hiding place of half the ordinary matter in the universe. The spinning filament that showed the web is in motion, handing its rotation to the galaxies within it. The Virgo bridge that caught the web in the act of starving a galaxy in real time, stripping its gas into a stream more than 1,000,000 light-years long, and the warped galaxies that prove the web bends the very shape of the galaxies inside it, including our own Milky Way. 5 discoveries. But here is the thing I've not yet said, the thing that makes all 5 together so much more powerful than any one of them alone. The way the warp study connected galaxy shape to the cosmic web is worth understanding in a little more detail, because it is a lovely piece of detective work. The researchers did not just notice that warped galaxies tend to sit near filaments and leave it there. They looked at the satellites of these galaxies as well, the smaller companion galaxies that orbit around the big ones, the way the Milky Way is orbited by its own retinue of smaller galaxies, and they found that in warped galaxies these satellites are not scattered randomly. They cluster at particular angles, arranged in a way that lines up with the larger structure of the cosmic web. In unwarped flat galaxies, the satellites are distributed differently, so the warp of a galaxy, the alignment of its satellites, and the orientation of the nearby cosmic web all turned out to be connected, woven together into a single consistent pattern. The shape of the galaxy, the arrangement of its companions, and its place in the web are all telling the same story, the story of the web's gravitational influence pressing on the galaxy and everything around it. This is what lets us be confident that the warp is genuinely caused by the web, rather than being some unrelated coincidence. When multiple independent features, the warp itself, the satellite distribution, the filament alignment, all line up consistently across hundreds of galaxies, you are no longer looking at chance. You're looking at a real physical effect, the tidal forces of the larger web reaching into galaxies and shaping them, bending their disks, arranging their companions, leaving a consistent signature that you can read across the whole population. The web's influence on galaxy shape is not a one-off curiosity. It is a systematic effect, written into galaxies wherever the web is dense enough to press upon them. And then there is the Milky Way, sitting squarely in the middle of this story. We know our galaxy is warped, mapped in exquisite detail by Gaia, and confirmed by other tracers. We know that warped galaxies tend to be the ones embedded in richer, denser parts of the web. Put those together, and the conclusion follows naturally. The Milky Way's warp is very plausibly the web's signature, pressed into our own galaxy, the same effect we see in hundreds of distant galaxies, operating right here at home. When you look up at the soft band of the Milky Way arching across a truly dark sky, far from any city lights, you're looking edge-on through the disk of our galaxy, and that disk is bent. The band you see is not a perfectly flat ring around you. It is warped, curled up on one side and down on the other, and that warp is the fingerprint of the largest structure in the universe, pressed into the shape of the galaxy that holds your sun and your world and you. There is a strange intimacy in that, when you really let it land. We have spent this whole video watching the web do things to distant strangers, to galaxies millions and billions of light-years away. It is easy to keep such things at a distance, to treat them as remote cosmic events with no bearing on us. But the warp will not let us do that. The warp is here. It is in our galaxy, in our sky, in the very shape of the home that made us. The same web that strips and starves and bends those distant galaxies as bent ours has left its mark on the structure we live inside. We are not watching the web from the outside like spectators at a vast and distant performance. We are inside it, shaped by it, our own galaxy bearing its fingerprint. The cosmic becomes personal, right here, written into the shape of the night sky above your head. Part 10. 5 lights, 1 structure. Step back with me now and look at what we have actually been doing through this entire story, because there is a pattern in it that is easy to miss when you are focused on each discovery one at a time. These 5 discoveries were not made by one telescope, or one team, or even one kind of light. They were made across the entire spectrum by completely different instruments, looking in completely different ways, and that turns out to matter enormously. The Cosmos Web Map was made in infrared light, the light of heat and distant things, caught by the great golden mirror of the James Webb Space Telescope 1,000,000 miles from Earth. The missing matter filament was found in X-rays, the light of the hottest and most violent gas, caught by the Suzaku and XMM Newton telescopes. The spinning filament and the Virgo gas bridge were both found in radio waves, the light given off by cold hydrogen gas, caught by enormous arrays of radio dishes in South Africa and Australia. And the warped galaxies were studied in visible light, the ordinary light your own eyes can see, mapped by the Gaia telescope and others, infrared, X-ray, radio, visible. 4 completely different kinds of light, 5 completely different instruments, separate teams of astronomers working independently, often not even in communication with one another, and they all turned out to be looking at the same thing. This is the part that should give you a particular kind of confidence, a confidence that is different from just believing one impressive result. When 5 independent lines of evidence, gathered in 4 different kinds of light by different people, using different instruments for different reasons, all converge on the same conclusion, that conclusion becomes very hard to dismiss. It is not one fluke. It is not one team seeing what they wanted to see. It is the universe telling the same story in 4 different languages, and the story comes out the same in every translation. The infrared says the web shapes galaxies. The X-rays say the web hides the universe's matter. The radio says the web moves and strips and starves. The visible light says the web bends the shapes of galaxies, including ours. And every one of those statements is a different facet of a single underlying truth. And that single truth is the thing this whole video has been building toward, so let me say it plainly now. The cosmic web is not a passive scaffold. It is not inert scenery. It is not a frame that simply holds galaxies in place while they live their independent lives. The cosmic web is an active driver of galactic evolution. It builds galaxies by funneling gas into the dense threads where the big galaxies grow. It hides most of the universe's ordinary matter in the hot diffuse gas of its filaments. It hands galaxies their spin, transferring rotation from its turning threads to the galaxies caught within them. It strips galaxies of their gas and starves them, killing them slowly as they fall into its dense regions. And it bends their shapes, pressing its tidal forces into their very form, warping their disks, including the disk of the Milky Way, feeding, hiding, spinning, starving, bending. 5 verbs, 5 discoveries, 1 structure. The web does not sit there. The web acts. Remember the city seen only by its lights, that image we started with so long ago. We thought the lit windows were the city, and we mapped the universe by those windows, by the galaxies, the bright furniture of the cosmos. But now the streets are lit too, the dark spaces between the windows, and we can finally see that the streets were never empty. The streets were where most of the city always was. The dark between the lights, the web between the galaxies was the real structure all along, and the galaxies were only its brightest and rarest ornaments. We spent a century studying the ornaments and calling it cosmology. Only now are we beginning to study the structure they hang upon. But there is one more layer to this, one more thing that these 5 discoveries together accomplish, and it reaches beyond the cosmic web itself into the deepest foundations of how we understand the universe. Because every one of these discoveries was also a test of the entire framework we use to make sense of the cosmos. And whether that framework passed or failed that test is the question we turn to next. It is worth pausing to honour what this convergence actually represents in terms of human effort, because it is easy to state the conclusion and miss the staggering collective achievement behind it. These 5 discoveries came from telescopes on 3 continents and in space, from a golden mirror a million miles from Earth, from X-ray observatories built by Japanese and European space agencies, from vast arrays of radio dishes spread across the deserts of South Africa and Australia, from a star mapping mission that measured 1 billion stars. They came from hundreds of scientists, engineers and technicians, most of whom never met one another, working in different countries, in different languages, with different instruments, toward different immediate goals. No one coordinated this. No single team set out to prove that the cosmic web is an active driver of galactic evolution. Each group was pursuing its own question in its own kind of light. And yet, when you lay their results side by side, they assemble themselves into a single coherent picture, as if they had been planned all along. That is one of the quiet glories of science, the way independent efforts, honestly pursued, converge on the same underlying truth without anyone arranging for them to. And the fact that the agreement comes across different kinds of light is what makes it so robust. Each kind of light has its own biases, its own blind spots, its own ways of potentially fooling you. Infrared sees certain things and misses others. X-rays reveal the hot and violent and overlook the cold and quiet. Radio catches the cold gas but not the hot. Visible light shows the stars but not the diffuse medium between them. Any single one of these taken alone could in principle be leading you astray, showing you a partial or distorted view. But when all four, with their completely different biases and blind spots, point to the same conclusion, the chance that you are being fooled drops to nearly nothing. The errors of one kind of light are not the errors of another. Where one is blind, another sees. And so the convergence across the spectrum is not just 5 pieces of evidence added together. It is 5 pieces of evidence that check and cross-examine one another, each covering the other's weaknesses, until what emerges is about as close to certainty as observational science ever gets. The cosmic web is an active driver of galaxy evolution. 4 kinds of light agree, and they agree precisely because they are different. Part 11. The test of everything. When astronomers built those great simulations we talked about earlier, Illustris and Illustris, TNG and the others, they were not just making pretty pictures of a make-believe universe. They were making predictions. They took our best understanding of how the universe works, the standard model of cosmology, with its dark matter and its dark energy and its patient gravity, and they let it run forward across simulated billions of years to see what kind of universe it would produce. And the universe it produced had specific, detailed, testable features. It had a web of a particular shape. It had filaments of a particular thickness. It predicted that ordinary matter would be hiding in those filaments as warm, hot gas. It predicted that galaxies would be sorted by the density of the web around them. It predicted that filaments could carry rotation. These were not vague hopes. They were concrete claims about what we should find if our understanding of the universe was correct. And now, finally, after all these years, we have been able to check those claims against reality. And here is the remarkable thing. The predictions are holding. The web that James Webb mapped looks like the web the simulations predicted. The missing matter turned up exactly where the simulation said it would be, as warm hot gas in the filaments, in just about the amount that was predicted. The relationship between galaxy mass and web density matches what the models forecast. Over and over, when we finally turned our instruments on the real cosmic web, we found the universe the standard model had described decades in advance. The guess, made on paper and in computers, turned out to match the sky. Let me put you in front of that comparison for a moment, because it is one of the quietly thrilling experiences in all of science. Imagine setting 2 images side by side on a screen. On the left, a simulation, a model universe grown inside a computer from nothing but the laws of physics and a set of starting conditions, the cosmic web as the standard model says it must be. On the right, the real thing, the actual cosmic web traced by the light of 164,000 real galaxies mapped by James Webb, and you look back and forth between them, left and right, simulation and reality. The same threads, the same nodes, the same dark voids opening between them, a pattern dreamed up from equations, sitting next to the same pattern read off the actual sky, and the 2 of them matching feature for feature, like a photograph held next to its own reflection. There is something almost eerie about it. A guess made decades ago in the abstract language of mathematics, turning out to describe the largest real structure in existence. That is what it looks like when a theory is right. That is the moment a model stops being a story we tell and becomes a description of the world. This is why these 5 discoveries matter beyond just the cosmic web itself. Because the standard model of cosmology rests on two of the strangest ideas in all of science: dark matter and dark energy, the invisible matter that builds the web skeleton, and the mysterious energy that drives the universe's expansion. These ideas make a lot of people uncomfortable, and understandably so. We are being asked to believe that the overwhelming majority of the universe is made of things we cannot see and do not understand. And whenever a theory leans that heavily on the invisible, it is fair, it is healthy, to ask whether the theory is really right, or whether we have simply invented unseen ingredients to paper over our ignorance. The cosmic web observations are one of the strongest answers to that worry, because the model that includes dark matter and dark energy predicted the web in detail, and the web turned out to match. You do not get predictions like that right by accident. A wrong theory does not casually forecast the precise structure of the largest thing in existence, and then have that forecast come true across the whole sky. Now, I want to be honest here. The way this channel always tries to be honest, because the temptation in a story like this is to wrap everything up too neatly, and the universe rarely cooperates with neat endings. The standard model passed these tests in its broad strokes, magnificently. But it is not perfect, and the same observations that confirm it in the large also reveal small cracks in the details. The precise way galaxies cluster together does not match the simulations perfectly. The detailed inner structure of some of those dark matter halos, the invisible clumps that galaxies sit inside, does not quite line up with what the models predict. These are not fatal flaws. They are not the kind of thing that overturns the whole framework, but they are real discrepancies, genuine mismatches between the model and the measurements, and they are exactly the kind of loose thread that, when scientists pull on it, tends to unravel into the next great discovery. The web confirms the standard model in its largest predictions, and at the very same time, it points toward the places where our understanding is still incomplete. And this is the right place to deal honestly with some of the stranger ideas that float around a structure like the cosmic web, because a thing this vast and this striking attracts them. You may have seen images of the cosmic web placed side by side with images of the neurons in a human brain, and the resemblance is genuinely uncanny. The branching threads, the dense nodes, the web-like connectivity, they look remarkably alike. And from that resemblance, some people draw a dramatic conclusion. The universe, they say, looks like a brain, so perhaps the universe is a brain. Perhaps the whole cosmos is some vast thinking thing, and the galaxies are its neurons firing, and we are living inside a single thought of a cosmic mind. It is a beautiful idea, and I understand its appeal completely. But the honest answer is that the resemblance is a coincidence of geometry, not evidence of a mind. Branching networks show up all over nature, in the way rivers carve their tributaries across a landscape, in the forking path of a lightning bolt, in the veins of a leaf, in the roots of a tree. They appear because branching is simply an efficient way for many natural processes to fill space and distribute flow. The cosmic web branches for the same kind of mathematical reason are river delta branches, because gravity pulling matter into filaments produces that shape, just as flowing water pulling itself downhill produces the river's shape. The pattern is real, but pattern is not the same as purpose. The web looks like a brain the way a river looks like a tree, by sharing the deep geometry of branching, not by sharing a mind. Then there is the suspicion that runs the other way. The idea that dark matter and dark energy are just fudge factors, numbers cosmologists invented to make their equations work, and that the cosmic web somehow proves the scientists are just fooling themselves with the elaborate curve fitting. But the story we have just walked through is the strongest possible answer to that suspicion, and it points in exactly the opposite direction. If dark matter were just a fudge factor with no reality to it, then a model built on it would have no business correctly predicting the detailed structure of the cosmic web before we ever saw it. The simulations made their predictions first, in advance, and the universe confirmed them afterward. That is the signature of a real theory describing real things, not the signature of people fooling themselves. And as for the missing matter, the suspicion that scientists somehow hid the numbers or made up the shortfall, the actual history is the opposite of a cover-up. The missing baryon problem was published openly, argued about in the open for decades, precisely because the numbers honestly did not add up and nobody pretended otherwise. And then the X-ray filament closed the gap with a direct detection of the missing gas, right where the honest, openly published predictions said it would be. That is not how a conspiracy behaves. That is how science behaves, slowly, openly, admitting what it does not know until the day it finally finds the answer. And honestly, the true story is stranger and more unsettling than any of the conspiracies. Nobody designed the cosmic web. No mind planned it. No intelligence arranged it. It emerged from nothing but gravity acting on matter across billions of years, the simplest force in the universe doing the same patient thing everywhere, all at once, for a very long time. And out of that blind, mindless process came a structure that ended up deciding the fate of every galaxy within it, including our own. That is more remarkable than a cosmic brain, not less. A universe that needed a designer to produce such intricate structure would be one kind of wonder. But a universe that produces this, the largest and most intricate structure in existence, the thing that feeds and starves and spins and bends entire galaxies, out of nothing but gravity and time and a few faint ripples in the early dark with no plan and no purpose behind it, that is a far deeper wonder. The web was not built, it grew, and it grew into the thing that made us possible. So the standard model stands, tested and largely confirmed by the very structure it predicted, with a handful of honest open questions still glittering at its edges like loose threads waiting to be pulled. That is a triumph, and we should not rush past it. For a century, the cosmic web was a prediction, a thing we believed in on the strength of theory and simulation. Now it is an observation, a place we have actually seen, and seeing it has confirmed that our deepest picture of the universe is, in its largest features, correct. But there is one final turn to this story, one last shift in perspective, and it is the one I have been saving for the end. Because for all that we have learned, for all that we have finally seen, the deepest lesson of the cosmic web is not really about the web at all. It is about us, and about what it means that we lived our entire history inside this structure without ever knowing it was there. It is worth being precise about why a successful prediction carries so much more weight than a successful explanation, because this is one of the deepest principles in how science earns our trust. It is always possible, after you already know the answer, to build a model that reproduces it. Give a clever enough person the result in advance, and they can usually find some set of assumptions that arrives at it. That kind of after-the-fact fitting is cheap, and scientists are rightly suspicious of it. But a genuine prediction is a completely different thing. A genuine prediction commits you, in advance, before you know the answer, to a specific claim about what you will find. And if that claim turns out to be right, especially if it is detailed and specific and turns out right across many independent measurements, then you have done something a mere explanation never could. You have shown that your model contains real information about the world, information it had before the world confirmed it. The cosmic web is exactly this kind of triumph. The simulations committed years in advance to a detailed picture of the web, its shape, its hidden gas, its sorting of galaxies, and then the real universe, observed at last, matched that committed picture. That is not curve fitting, that is prophecy, the scientific kind, the kind that earns a theory the right to be believed. But the honest scientist holds two things at once, and I want to model that here rather than pretend the picture is tidier than it is. The standard model predicted the web, and the web matched, magnificently, in its large-scale features. And at the same time, in the fine details, there are mismatches that no honest account should bury. The precise statistics of how galaxies cluster together at small scales do not line up perfectly with the simulations. The detailed inner structure of dark matter halos, those invisible clumps galaxies nest inside, shows discrepancies between what the models predict and what the measurements suggest. These are not catastrophes. They do not threaten the broad framework, which has now passed too many tests for that. But they are real, and they are precisely the kind of small persistent anomaly that historically has been the seed of the next revolution in physics. The greatest discoveries often begin not with a dramatic failure of a theory, but with a small, stubborn discrepancy that refuses to go away, a tiny mismatch that, when finally understood, cracks open a whole new layer of reality. The cosmic web confirms our deepest picture of the universe and, in the same breath, points its finger at the places where that picture is still incomplete. Both things are true. Both things matter. This is, in the end, what good science actually looks like, and it is worth saying clearly because it is so often misunderstood. Science is not a finished body of certain facts handed down from on high. It is a living process of prediction and test, of confidence and honest doubt held together. The cosmic web story shows you that process working at its very best. A bold theory, leaning on invisible ingredients that make people uncomfortable, makes detailed predictions about the largest structure in existence. New instruments, working across 4 kinds of light, finally test those predictions. The big predictions pass, triumphantly, vindicating the framework and the strange invisible ingredients it rests upon. And the small discrepancies that remain are not hidden or explained away but noted honestly, marked as the frontier where the next discoveries will be made. That is not weakness. That is exactly how knowledge is supposed to grow, one tested prediction and one honest open question at a time. Part 12. Standing inside the main character. Let me return us to where we began, to that image of the invisible city, of standing inside an enormous structure you cannot see. We have spent this whole journey learning to see it, and now I want to ask what it actually means that the structure was invisible to us for so long, because I think that fact, more than any single discovery, is the thing worth carrying away from tonight. For the entire history of human astronomy, from the first person who ever looked up and tried to make sense of the lights in the sky, all the way through the great observatories of the last century, the largest and most influential structure in the universe was completely hidden from us. We mapped the planets, we charted the stars, we measured the distances to galaxies and traced the expansion of the cosmos and peered back toward the moment of the Big Bang itself. And through all of it, the cosmic web, the thing that decided whether our galaxy would live or die, where it would sit, how fast it would spin, what shape it would take, was invisible. We were living inside it. We were shaped by it, and we were blind to it. It is one thing to be ignorant of some distant phenomenon, some far-off corner of the cosmos that does not touch us. It is another thing entirely to be ignorant of the structure you are standing inside, the structure that made your home what it is. Think about everything we have learned tonight, and then turn each of those lessons back toward our own galaxy, toward the Milky Way, toward home. The web feeds galaxies in its rich strands, and the Milky Way grew massive enough to make the sun because it formed on a strand rich enough to feed it. The web starves galaxies that fall into its dense knots, and the Milky Way has so far avoided that fate, kept its gas gone on making stars long enough for one of those stars to be the sun, with the Earth in orbit around it, and you on the Earth. The web hands galaxies their spin, and the rotation of the Milky Way, the great wheeling of the disk that carries the sun around the galactic centre, once every couple 100 million years, may be an inheritance handed down from the web itself. And the web bends the shapes of galaxies, and the Milky Way is warped, its disk bent by the web's tidal hand, carrying that fingerprint in its very form. Every single thing the web does to galaxies, it has done to ours. The web decided where our galaxy sits, how fast it spins, what shape it takes, and whether it kept the gas long enough to make the sun. And we learned that the web existed as a thing we could actually look at and study, only in the last few months, sit with the full weight of that. Everything about our cosmic home, the position, the rotation, the shape, the very survival of the galaxy that made us, was determined by a structure we could not see until almost the present moment. The universe we thought we understood, The universe of stars and planets and galaxies, the bright furniture of the cosmos, turns out to have been only its visible surface. The real structure, the thing that governs all of it, was hidden in the dark between the lights, and we are only now beginning to see it. We have been like a fish that has finally, after a lifetime, become aware of the water. The water was always there. The water shaped everything, and the fish never knew. This is the great inversion that the cosmic web forces on us, and it is the deepest idea in this entire story. For a century, we treated galaxies as the real objects, and the space between them as empty, as nothing, as mere backdrop. These discoveries reverse that completely. Most of the ordinary matter lives in the web between the galaxies, not in the galaxies themselves. Most of the structure is in the threads, not in the knots. The origin of galactic spin and the shaping of galactic form may both come from the web, not from within the galaxies at all. The galaxies, those bright cities of stars we spent a century studying, are the exceptions. They are the rare bright islands rising out of a vast and mostly invisible ocean. The web is the rule. The web was always the rule, and we mistook the islands for the world. We were standing inside it the whole time. That phrase has travelled with us through this entire journey, and look at what it has become. At the start, it was just a statement about ignorance, a fact that we had not yet noticed the web around us. But now it is the emotional heart of everything. We were never observers of the cosmic web, studying it safely from outside. We were always residents of it, formed within it, shaped by it, our galaxy bent by its hand, our existence downstream of its geography. We did not discover the web the way an explorer discovers a new land across the sea. We woke up to it, finally, the way you might wake in a dark room and slowly realize as your eyes adjust that the room is far larger than you ever knew, and that you have been living in it your whole life, and that it has been quietly shaping you all along. And so, we are left with a question, the kind of question this channel loves, the kind with no tidy answer, the kind you carry with you after the video ends and turn over in the dark before sleep. If the single largest and most influential structure in the universe, the thing that governs the life and death and shape and spin of every galaxy, including our own, was completely hidden from us until just a few months ago, then what does it actually mean to say that we understand the universe? What else is out there? Larger than we imagine, closer than we think, shaping us in ways we have not yet learned to see. We only just met the skeleton of the cosmos. We have only just turned on the lights in the one room we have lived in all along. And if it took us this long to see the structure we are standing inside, then the honest truth is that we do not yet know how much more there is, hidden in the dark between the lights, waiting for the next instrument, the next survey, the next quiet evening when an image resolves on a screen and a human being becomes the first to see something that was always there. The cosmic web was always there. We simply could not see it. And the deepest lesson it offers is not an answer at all. It is the humbling, wondrous, slightly unsettling reminder that the universe we thought we knew was only its surface, and that beneath that surface, in the dark we are only beginning to map. The real architecture of everything has been waiting, patient as gravity, for us to finally open our eyes. There is a particular feeling that comes with a realization like this, and it is worth naming, because it is the feeling this whole channel exists to find. It is not fear, exactly, though there is an edge of unease in it. It is not joy, exactly, though there is wonder in it. It is something closer to humility, the specific humility that comes from suddenly seeing how much larger and stranger the world is than you had assumed, and how much of it was operating all this time just beyond the edge of your perception. It is the feeling of a child who realizes for the first time that the adults around them have entire inner lives they know nothing about, that the world is full of depth they had never suspected. The cosmic web gives us that feeling at the scale of the entire universe. We thought we had the shape of things. We had the galaxies mapped, the expansion measured, the broad history sketched. And then we learned that the thing organizing all of it, the structure governing the fate of every galaxy, including our own, had been invisible to us the entire time. The world was deeper than we knew. It always is. And I find there is a strange comfort folded inside that humility, alongside the unease, and I want to leave you with it rather than with the unease alone. Because the lesson of the cosmic web is not that we are small and the universe is indifferent, though both of those things may be true. The lesson is that we are capable of seeing it at all. Think about what it actually took. A species on a small planet, orbiting an ordinary star on one bead of one strand of this incomprehensibly vast web, managed to build instruments that could finally perceive the structure it was embedded in. We were inside the web, shaped by it, blind to it, and we reasoned and built and observed our way to seeing it anyway. We turned on the lights in the room we had lived in all our lives. That is not a small thing. A universe that produces, out of blind gravity and patient time, a creature able to look up and finally comprehend the architecture of everything, is a universe with a quiet kind of grandeur to it, even if no one designed it, even if it means nothing by what it does. We are the part of the cosmic web that learned to see itself. After nearly 14 billion years, the web grew something on one of its countless beads that could look back at the whole and understand a little of what it was looking at. So tonight, when you finally let your eyes close, I want you to carry one image with you into the dark. Picture the web again, the whole vast glittering lattice of it, threads and nodes and voids reaching across the entire observable universe, the missing matter glowing faintly in its filaments, the great structures slowly turning, galaxies being fed and starved and bent all across its span. And then find, somewhere in that immensity, one ordinary strand, and on that strand, one bright bead among countless others, and inside that bead, on a small warm world circling an unremarkable star, picture yourself lying here at the end of a long day, having just learned that you were never floating free in empty space at all. You were always held, always shaped, always woven into the largest structure there is. You were standing inside it the whole time, and now, at last, you know,